Well, today I'd like to talk about the r theta z coordinate system, and this coordinate system is especially useful for a lot of circular or spiral kinds of motion, a lot of motors, carnival rides, cams, quite a few mechanisms and radar tracking systems, etc. Those are often described by, the position would be described by a distance from an origin and an angle. The particle moves along a moves along a curved path. Doesn't have to be a circular path, but a curved path. But if the position is being tracked, or if position is being defined as a distance and an angle, then the r theta z system can be quite helpful. Now, how do we describe the coordinate system? There will be an origin of some point that the position will be looked at. The axis travels along with the particle along the curved path, just like the NTB coordinate system. The direction of the r-axis will be positive in increasing r away from the origin. So if the origin is here, or the reference point is here, the particle is here, then increasing r goes that way. So positive r-axis begins at the particle and will go positive that way. The theta axis will be perpendicular to the r-axis. Now, the direction of the theta axis, whether it goes that way or this way, depends on the definition of theta. If theta is defined as, and you'll usually see an angle with an arrow on one end, but sometimes you won't, but usually you'll have the angle with the arrow at one end, which means it's increasing theta or positive theta going in that direction. So we'll want to define the positive theta axis in the same direction as increasing theta. And again, it emanates from the particle itself. So our axis begins there, theta axis is perpendicular and positive in that direction. The z-axis, and we may find the z-axis useful, but the z-axis would come out of the page, and it would be positive z in either direction. We can define it as we need to. Okay, again, like the NTB coordinate system, the coordinate axis travels with the particle, but all the coordinate systems, whether we're talking about x, y, z, r theta z, or NTB, they all have three axes, or three mutually perpendicular axes. We usually define the coordinate system in terms of the plane defined by xy, or r theta, or nt, and then the z-axis here and the b-axis here are going to be what's perpendicular to the plane, and that'll be what we'll again consider here. Also, remember that the actual velocity and the actual acceleration, actual meaning the square root of the sum of the squares of whatever the components are, those are always going to be the same regardless of what coordinate system we use to define. And we'll get used to calculating that and comparing those a little bit. Well, what is r theta really? Well, if you have this plate here that's rotating in this direction, maybe we have a ball in a slot also traveling that way. Well, you can see that the ball, if the plate is rotating this way, the ball has both radial speed, meaning it's moving out this way, and it has angular speed as well, which means that theta, there's going to be a theta dot going that way. So the way we're going to define this is that r will be positive emanating out from the center, be positive r going that way. R dot will be the speed away from the center, and r double dot will be the acceleration away from the center. Theta will be the angle. Angle will be defined by some starting point or some reference point. We may say that that'll be the start. If that is positive theta going in this direction, then as it changes, we'll have a theta dot, or angular velocity or angular speed. If it's accelerating, then we'll have a theta double dot, or an angular acceleration. We'll get used to doing those things. Okay. We may also have something that looks like this, where this would be a rod and a slider. The rod may be moving in an angular direction, but the slider, if it slides along this rod, will have both an angular component and a radial, or an r component. So again, we'll define the position as an r away from the origin and some angle, and then our axis will be emanating from the slider going out away from that. If theta is positive going in this direction, then theta positive will go in that direction. A couple things to note. If r is fixed, in other words, r dot and r double dot are 0, then all we're doing is we're sticking right there in that spot. We may still be rotating around in the middle, but that would say that that is circular motion if r and r double dot are equal to 0. Similarly, if theta wasn't changing, but we did have some movement in the r direction, then all we do is we just have straight line motion along that rod. So if theta dot and theta double dot are equal to 0, then the motion is just straight out from the center. Clearly, in order to make the problems interesting, we have a combination of r's and thetas that are both have some amounts of r dot and r double dot, so usually a combination. Okay, so we're going to talk about theta, theta dot, theta double dot, again, which are the first derivatives. Remember, our dots are the derivative with respect to time. Often the thetas and the r's are defined as functions of time, so when that happens, it's very easy to take derivatives or integrals to find out what the other ones are if they are functions of time, just like we've done before. Remember that theta is in radians, and so theta dot would be radians per second, theta double dot would be radians per second squared. R dot, and R double dot are all going to be units of length. Now once we find those components, then we can find the actual velocities and the actual accelerations in those directions. And these are not as intuitive as x dot and x double dot, y dot and y double dot. Maybe in the radial direction maybe for velocity it makes pretty good sense, because velocity in the r direction would be just whatever the velocity is, or just the r dot. The velocity in the theta direction is defined as r theta dot. Accelerations are definitely not intuitive, and we'll study more about what these equations mean and how they are derived as we go forward, especially in chapter 13. But for right now, let's just focus on the math, and we're going to say that the acceleration in the r direction is defined as r double dot minus r theta dot squared, and acceleration in the theta direction is r theta double dot plus 2r dot theta dot. Again, once we find those components, and then we can find the actual magnitude and the actual actual magnitude of velocity, the actual magnitude of acceleration by taking the square root of the sum of the squares. Always remember that the actual velocity is tangent to the path, the actual acceleration is generally not tangent to the path. Recognize also that the problem lends itself to r theta if the position is described by r theta, as I said before. One thing we should note is that as the particle moves on its curved path, where it's if theta is defined as a positive in this direction, then the theta axis goes in that direction, as we said before. However, the angle actually may be decreasing as a function of time. In other words, it may be moving in this direction. So it's definitely possible to have the positive theta axis going this way, but when we find our velocities and our angular accelerations, they could be negative. So we could have theta dot and theta double dot negative. The same thing with r. If r is going positive away from the origin, so r axis is going that way. However, if the particle is moving back toward the origin as a function of the radial direction, we could easily have r dot and r double dot negative. And we could have them be positive, it could be combinations of positive and negative. In other words, one of them could be positive, the other one could be negative, fairly easy. Another thing to remember is that another thing to note, I guess I haven't mentioned it yet, but that the r theta z system is really a great method to describe spiral motion, whether it's a spiral going up around a circle, or it could be a conical shape where the radius is increasing. So spiral motion is an excellent r theta z type of description. Just a couple things about dynamics speak is that radial means the r-axis. Sometimes you'll see transverse as a word here, and transverse means the theta axis. Well, I'd like to go through a few problems with you. Here's a fundamental problem, F12-34. And this is same problems I was referring to in the previous section, but this plate is rotating in this direction. It's got a reference here. The ball is sliding out in this slot, so it's moving out and rotating in kind of a spiral fashion. And we're looking for the value of the velocity and the acceleration at a particular point. So it says that theta is defined as a function of time, 4t to the 3/2. R is also defined as a function of time, 0.1 t cubed. So when both of them are defined as a function of time, it's fairly easy to do the evaluation. But what I'd like to do is set this up in a table format. That's a really good method for handling these types of problems. And what we're looking for, again, is the components of the velocity and the acceleration. So we're looking for theta, theta dot, theta double dot, r, r dot, and r double dot. And if we put them in a table format and evaluate them like that, it's fairly simple. All right, so let's start with theta. Theta is equal to 4t to the 3 halves. Theta dot is just the time derivative of that, so it'll be 4 times 3 halves, t to the 1 half, evaluated, 6t to the 1 half. Theta double dot is this derivative with respect to time, so that'd be 6 1 half, t to the minus 1 half is equal to 3t to the minus 1 half. Now I can evaluate this, like I said, in a table format at t equals 1.5, because that's what we're looking for. The end of the problem is when t is equal to 1.5. So plug in 1.5 into each of these, and I can evaluate that. Theta is going to be 7.35 radians, so it's kind of gone a couple of revolutions, I guess. 2 pi radians is 1 revolution, so that would be around 2 revolutions. 7.35 radians per second would be my theta dot, and theta double dot would be 2.45. Now let's look at r. R is also defined as a function of time, given in the problem is 0.1 t cubed. Taking the derivative, r dot is equal to 0.3 t squared, r double dot is 0.6 t. Evaluating those, we get those values. So once we find the components, the actual numerical values of each of these guys, and remember thetas are going to be defined in radians, radians per second squared, and the r's are going to be in meters or feet, some sort of length per second and second squared. After we get those components, we just plug it straight into these equations. It's very plug and chug, this section is. So you just kind of get those components by doing a little bit of math and then plug them into these formulas and do some arithmetic. It's real simple. So velocity of r is r dot, and we get that from straight up here. Velocity of theta is r theta double dot. So I get r times theta dot, and I get 2.48 meters per second. Both of these velocities are in meters per second. Acceleration in the radial direction, r double dot minus r theta dot squared. Plugging those in from the table above, I get negative 17.33. And a theta, acceleration in the theta direction, r theta double dot plus 2 r dot theta dot. Plugging those in from the table above, I get 10.75. Now, the units on both of these guys are going to be meters per second squared. So again, we got meters per second for velocity and meters per second squared. Even though the units of the thetas are going to be in radians, the units of the velocities and accelerations are in terms of length. Finding the magnitude then is easy. Just plug these two values and take the square root of the sum of the squares, basically do the vector sum, and we get the magnitude of the velocity of 2.57. The magnitude of those two components of the acceleration is 20.4 meters per second squared. All right, this one's just a little bit different. This is more of a rod and a slider. We'll see this a lot in a lot of real mechanisms. But again, we're looking for the velocity and acceleration at some time in the future, and or at some time that's specified in the problem. And let's look at the definitions here. It says that velocity, angular velocity, theta dot, is 6 radians per second, and it's constant. That makes the problem fairly easy, because if theta dot is constant, that means that theta double dot is going to be equal to 0. We still have to calculate theta through here. The ending theta is not given, but the ending time is given. So we'll see where we can get from there. R dot is given as 4t squared, again a function of time, so fairly easy to take a derivative and an integral to find r double dot and r. So let's proceed. Again, set this up in a table, and we're going to start with theta dot is equal to 6 constant, theta double dot is equal to 0. Theta is going to be the integral of theta dot dt, so that's equal to 6t. Evaluating that at t is equal to 0.75 seconds, and you can get those values. R dot is equal to 4t squared. Taking the derivative, you get 8t. And finding r, we take the integral. So we get the integral of r dot dt, so the integral of 4t squared dt, so that's 4t cubed over 3. Evaluating each of these at t is equal to 0.5, fairly easy, just plug things in and get those numbers, and you get those values there. Then to find the velocities, again, very simple. Just take vr is equal to r dot, get that from the table above. Velocity in the theta direction, r theta dot, get those two components from the table above, and velocity in the magnitude of the velocity is the square root of the sum of those two pieces. the sum of those squares is equal to 4.06. So vector sum, vector addition of that. Okay. Now, acceleration, same thing. R double dot minus r theta dot squared, taking those from the table above. Our acceleration in the theta direction, r theta double dot plus 2r dot theta dot, get those from the table above. In this case, r double dot, or excuse me, theta double dot was equal to 0. So one of the terms was equal to 0 in this calculation. We'll find that occasionally in some of the problems where the arithmetic will be a little simpler. Again, we'll get a negative number here for acceleration in the r direction, a positive number for acceleration in the theta direction, and we'll get a mag is equal to the square root of the sum of those squares. Okay. Last one, let's do this one together just a little bit. Here's a spiral slot. You can see what we've got here is a spiral path that's being defined. That's where the particle is going to go. And the particle has to move back and forth in this slot and also in this path, in this slot it looks like. Here's the little particle, it's a little ball here. And what's going on is this, as this slot here rotates in this direction, it forces the particle to go up and through there. So our question is at a particular time, it's actually when the particle actually reaches the end of this, which is going to be up in this angle someplace, what's the velocity and the magnitude? The theta dot here is given as 3. Looks like it's a constant, so that makes that easy. And the position of r is given as a function of theta. So we'll have to do just a little bit of different work here. But again, we'll set this up in a table and see what we get. Theta dot is equal to 3, which is equal to a constant, which makes theta double dot equal to 0. So just from our understanding here, it's going to be that. So theta, what is theta? I don't have enough information here. I can say it's 3t, but I don't know what time is. The end of the problem is given as r is equal to 0.5. So since these are not functions of time or easily put in function of time, and my ending condition is a function of the position r, I'm going to leave that blank for right now. So let's go down to r. We're going to say r, as given in the problem, is equal to 0.4 theta. And we can take the derivative of both sides here. Now we get r as a function of time. I mean, that's what these dots are. And we can get this as a function of time since there's no other terms here. So r dot is equal to 0.4 theta dot, and r double dot is 0.4 theta double dot. So that's fairly easy. Now, what can we do? We are given r as a function of, or we're given at the end of the problem, r is equal to 0.5. So that's fairly easy. We'll just put 0.5 in there. R dot is given as a function of theta. Well, we still don't know what that theta is, except that we've got a function here, or a number that we can evaluate theta at by saying r is equal to 0.5. I can solve that for theta. So when I do that, I see that theta is equal to 1.25. So theta is equal to 0.5 divided by 0.4. So I'm going to say that that's equal to 1.25 radians right there. All right. Now, what's r dot? R dot is equal to 0.4 times theta dot. Theta dot is given there, so that gives me r dot as 0.4. I'm sorry, not 0.04. 0.4 times 3, and that's equal to 1.2. And r double dot is equal to 0.4 theta double dot, but theta double dot was equal to 0, so that's going to be equal to 0. All right, so now I've got all the values in my table. I should put some units here. Theta is going to be radians per second, and this will be radians. This will be meters, I believe. Is this where it's at? We need to look carefully. Yeah, meters. So that'd be 0.5 meters. This would be meters per second, and this would be 0. All right, plugging those things now into our equations is pretty simple. All we have to do is r dot is equal to, from the table, is 1.2. R theta dot is equal to 0.5, and theta dot is equal to 3. So that's equal to 1.5. And the square root of the sum of the squares of that is equal to 1.2921 meters per second. So that's the answer that we'd be looking for. All right, how about acceleration in the r direction? R double dot minus r theta dot squared. Now r double dot was equal to 0, so that makes that term easy. Minus r is 0.5. And theta dot squared is 3 squared. And so that's equal to negative 4.5. A theta, r is 0.5. And theta double dot is equal to 0. Oh, good. So we got another 0 term there. Plus 2r dot, and that would be 1.2. And theta dot is 3. And that's equal to 7.2. All right, so getting all those values there, then taking the square root of the sum of the squares, that's pretty easy. And that is equal to, did I calculate that? I didn't calculate that. So that's equal to, well, let me just do it right now. Square root would be 4.5 squared plus 7.2 squared. And that's equal to, calculator come alive here, 4.5 squared, 7.2 squared, plus square root, that would be 8.49. And both of those are going to be, this is all in meters per second squared. Anyway, that's a good way to set things up in a table method, and you can keep your work nice and organized that way, and that's the way I would like you to do it in your homework and on the exams.